Hey AP Chemsters, this is Mrs. Vanderlei again bringing you 9.6. This is a very important section. I hope you read through it and took your notes. Unfortunately, many of the pictures did not get transferred over to the smart board. We're having major computer issues here at the school today, so I had to draw them in. Excuse me for my bad drawings, but yeah, there's no pictures here, so just bear with it. So let's talk about this. It says the limitations of the Lewis dot diagram. We understand, in a sense, when you have Lewis dot diagrams, how bonding occurs, how many hydrogens will bond with oxygen, or in this case, how many hydrogens will bond with fluorine. What it doesn't really do is show you the full picture. Are those electrons between the hydrogen and fluorine, these right here, are these truly, let me just circle here, are they smack dab in the middle between the hydrogen and the fluorine? That's a great question. The answer ends up being no. If you recall, fluorine was the most electronegative element there was. It was a 4.0. It was the greatest electron loving, had the greatest electron affinity of all the elements. So it is will strongly attract the electrons towards it physically. So if we could get like a little microscope going and checking out where those electrons are, we will see these electrons are much, much, much closer to fluorine than the hydrogen. And so because of that, it has a special, unique characteristic. And that talks about this idea of polarity. A polar bond a polar bond in this case is where we have an unequal sharing of electrons. So it says, look at here, the electrons, it looks like, are equally shared. It's not the case. So instead, for reasons that I said, the fluorine has a much higher electron affinity. The electrons are literally closer to the fluorine atom than the hydrogen atom. And we have two ways of showing this, okay? The first way, in a sense, has the arrow going to the more electron-loving element. And that's what this is. The little dash there kind of shows you it's going from one direction to the other one. Probably the way that I do, and I'm not sure about Mrs. Blankenship, I use these other little symbols, which are a partial. It is actually in the Greek alphabet a lowercase delta. And so this lowercase delta is a partial symbol. So it means partially positive, partially negative. So if you think about that, if the fluorine is attracting the electrons closer to it, and the electrons are negatively charged, that means the fluorine takes on a more negative charge around it. Not fully, but partially. So we would draw this. Here is your partially negative fluorine. And so that means it has those electrons closer to it, becoming partially negative. But what about the hydrogen? The hydrogen is losing its proximity to the electrons. So it's becoming less negative, and if it's becoming less negative, it's becoming more positive. So the H is partially positive, and then the fluorine is partially negative. So that's the way I will be drawing it more. I believe it's probably more common than the arrows, although the arrows you might see every now and then. And how do we know this really works? How can we actually prove what I'm saying? Well, these things right here, these black plates, that's what these things are. These are your black plates. This is like a magnetic field. So if I put these plates on, turn on the electricity, make the magnetic field go, all right, what's going to happen? Well, the before shot, all right, notice that there's kind of like a random motion to the hydrogen fluoride molecule. The H's are showing all different directions. The fluoride is all, fluorine is all different directions. So that's before the plate is actually turned on. So the after shot, notice, here's your after. Okay, I turn on this magnetic field, zoom, all right, and notice this plate is my negative plate, and this plate is my positive plate. And look at how these molecules line up. Notice in each case that the hydrogen right here, here's the hydrogen, here's the hydrogen, Here's the hydrogen. The hydrogen that is partially positive aligns itself to the negative plate. The partially negative fluorine aligns itself to the more positive plate. So it's like a magnet lining itself up. Folks, I truly did not mean to have more of the molecules more on the left than on the right. They will be more dispersed more evenly. So you might have a couple molecules closer to the positive plate. That was just my quick drawing efforts. If you look at your picture, you'll see that's more like what we're looking at. So let me turn the page. Okay, so now we're talking about this uneven distribution of electrical charge. That is by definition a polar covalent bond. And we said careful sharing is hardly ever 50-50. There are cases where that's the case, okay? When we have equally loving atoms, such as in a fluorine-fluorine bond or an oxygen-oxygen bond, there you have each oxygen, each fluorine loving them equally, but that's not really the case most often. Usually one will love these electrons more, have a great electronegativity, greater electron affinity. So that's your polar covalent bond. Please get used to hearing polar means unequally sharing, okay? So it's classified as a polar covalent as they're unequally sharing the electrons, that the electrons are much more closer to the fluorine than the hydrogen, because fluorine is the most electron loving. So I said, remember, a complete transfer of electrons is an ionic bond. So again, how can you tell if we have an ionic bond, a polar covalent bond, or a non-polar covalent bond? Again, nonpolar is equally sharing. You must look at the electronegativities. Now again, as I explained a little bit earlier, we're having internet issues. My pictures did not transfer over. So you should be looking at this diagram of the electronegativity values yourself, okay? And part B, oh my goodness, I can't tell you how important this is. And the AP does not expect you to memorize these values. You don't have to know fluorine is 4.0, oxygen's 3.5, and nitrogen and chlorine are tied at 3.0, but you have to know those are the big four, and they do expect you to recognize those as being the four most electron-loving elements there are, okay? So if you look at your diagram, you will see that fluorine's at the top, okay? So the question is, all right, which element has the greatest electronegativity? Well, I hope you know that's fluorine. Okay, the question is, well, why? Okay, what is electronegativity about? It's really a measure of the attraction of bond. Well, what did we say that the measure of attraction was about? It has, you could say, the most effective nuclear charge. It has the fewest shells, so it has the closest proximity to the nucleus. It has almost a filled shell. And so if you gain an electron, it will have a filled shell, creating that stability. So it does have, in its shell, it does have 7 electrons in the outer shell, bringing it closer, you know, in a sense, to that proton, the nucleus with the 9 protons. So for all the same reasons of periodic trends, that's why fluorine has the greatest electronegativity. Let me scooch this up a little bit. All right, so which element has the lowest electronegativity? Well, where is the width of the tiles the lowest? Hopefully you'll see, I believe it's francium. Okay, and why is it? It's for the same reason we talked about in periodic trends. It has the least effective nuclear charge. It has the fewest protons in its nucleus compared to the other members of its shell, and it has its electrons by far the furthest away. It is 7 shells away from the nucleus. So the proximity and the fewest amount of protons for that shell makes it why it has the lowest attraction for that. Now you can also look, fluorine is a nonmetal, francium is a metal. All those reasons play into that. So why are the noble gases not included on this chart? Well, they would have the greatest effective nuclear charge, wouldn't they? They have the most amount of protons in its nucleus compared, you know, to other members of its shells. But again, what are we doing? Does the noble gas, can it accept another electron? And that's what we're asking it to do. We talk about electronegativity, really. And the answer is no. It has a filled shell already. it does not require another electron to make it stable. So if you think about it, where would that next electron go? It would have to create a new shell for that, especially the smaller ones. The larger ones would have to start filling in its D shell. So it's not included. It doesn't really have electronegativity values. If you look though on other charts, you'll see the larger ones like, radon does have a measurable electronegativity, but it's still lower than what the other nonmetals would be. What is the trend going across the period? Well, if you look closely, it looks like these little tiles are getting higher and higher. The electronegativity is definitely increasing. Why? Greater effective nuclear charge. What about the trend going down a group? The electronegativity is going down. Hope we can see that the bottom rows have the lowest numbers. Why is that? Well, they're further away, more shells. So it says arrange these elements in order of decreasing. So in other words, put the most electronegative first and then the least electronegative last. So I'll give you a minute if you haven't done already. Think about it and see how you do. All right, hope we got that. Nitrogen is one of the big four, so that should have jumped out at you. Phosphorus is also a nonmetal in the third shell. Then aluminum, then sodium. Notice that sodium has fewer protons than any of those in its shell, so it has the least electronegativity. All right, let's turn the page. So what does this electronegativity do for us? It really helps us zero in on, are we talking about nonpolar, polar, or ionic? So there's our description. Nonpolar is equal sharing, has electronegativity of 0 to about, that's what that little squiggle line means, about 0.4. So electronegativity difference, you are subtracting the two values of electronegativity, and if they get around 0 to 0.4, it's going to be nonpolar. That's basically sharing, equally sharing. Rule of thumb is either the same nonmetal elements or very close to each other on the periodic table. For example, chlorine, and then you can see your picture that didn't show up on my smartboard. Polar covalent has a nice wide range. It's unequally sharing electrons. These are getting those deltas, those partials there. If you subtract the two numbers, you're getting about 0.4 to about 2.0. Again, there's some gray areas. What's happening here? Nonmetals, but not close to each other on the periodic table. And for example, HCl. If you look in your chart, H is 2.1, chlorine is 3.0. You subtract the two, you get 0.9. It's in that range. And there's your picture. An ionic bond is not sharing electrons, but giving and taking. Excuse me. You have an electronegativity difference of greater than about 2.0. Metal, nonmetal, sodium chloride. Now, notice those little gray areas, those little squiggle marks. That is, again, the gray area. How can you definitively tell? Well, the best way to definitively tell if it's ionic or covalent is to melt them. And if you melt their solids, usually at very, very high temperatures, and they conduct, that's when you know it's ionic. If it doesn't conduct, it is covalent. But otherwise, these rule of thumbs and these little gray areas, we'll probably just go with what we have here as far as the rule of thumb, and that's what you need to know. Metal, nonmetal, ionic. Nonmetal is not very close to each other, is going to be polar, and then over here is going to be your nonpolars. Again, the important thing you know is your big four. Let's go down. Okay. Notice that my picture is gone again, and this is another picture of what we're talking about. So this is determine whether the bonds formed between each pair is nonpolar, polar, or ionic. So strontium and fluorine, what do you think? Strontium is a metal, fluorine is a nonmetal. It should be, yes, ionic. N and Cl, they are two nonmetals, so I automatically know it's going to be covalent. So are they close to each other or not? They're going to be nonpolar covalent. Actually, electronegativity values are equal to each other as 3.0. So that's going to be your subtract to get 0, and that's going to be nonpolar. Finally, N and O, they are next to each other, but because oxygen is the second most electron loving, it ends up being polar covalent. So let me write this down. Ionic, nonpolar covalent, polar covalent. So look at their electronegativities. Again, I'll put these here, and you subtract at 0. This is 3, this is 3.5, you get 0.5. Always make it a positive number when you subtract. I'm out. Look for the next one.